Are we live yet? We are live. Excellent. Okay. So, we finished last time by talking about state functions versus path functions, where a state function, all that matters is where you are, and a path function, matters how you get there. Now we're going to talk about system versus surroundings. Okay. So, as I mentioned last time, we can talk about systems being open, closed, or isolated. Or an open system, energy and matter can move in or out, not a problem. And this thus applies to everything in the universe. A closed system, matter cannot move, but energy can go in or out. So, hypothetical, just a really awesome closed bottle or a box. A lot of things come really close to a closed system. An isolated system, neither energy nor matter can get in or out, and really nothing actually does this. The universe is an isolated system. Actually, let me double check. Yes, okay, you can hear me. The universe is a closed system, and that's about it. Okay, we can get really close to an isolated system, though. And the reason we do this is math stuff. Okay. So now, the system versus the surroundings. The system is the thing we care about. So in chemistry, it's usually going to be a chemical reaction of some kind. The surroundings is literally everything. Dang it, Dog. The surroundings is literally everything else in the entire universe. So, what this means is that because the universe is an isolated system, the energy of the universe is constant. So the change in energy of the system plus the change in energy of the surroundings will be equal to the change in energy of the universe. And thus, it will be equal to zero. Which means that the change in energy of the system is going to be equal and opposite the change in energy of the surroundings. So notice this negative sign here. So this is why, one of the reasons why we care about isolated systems and so on, because this is a pretty big deal. Okay, this is one of the expressions of the first law of thermodynamics, namely that the change in energy of a system will be equal to negative the change of the energy of the surroundings. So if you measure one, you've measured the other. Measuring the surroundings means measuring the system. Okay, so if you can measure the entire universe, you can also measure the system. But the thing is, obviously, you can't do that. But if you're smart about how you set things up, you can measure a small bit of the surroundings, and that'll be good enough. And that is the basis for calorimetry, which is measuring the movement of heat in or out of a system. This is a really powerful tool for studying chemical reactions. Now, sign conventions. Chemists are good, moral people. We care about the system. Physicists are perverts who care about the surroundings. So, for us, energy moving into a system has a positive sign. Energy moving out of a system, we give it a negative sign. So, look at, for example, combustion. Here we have methane combining with oxygen to make CO2 and H2O. This is an exothermic reaction. It releases a lot of energy as heat and flame. The change in energy is negative. So, negative sign right there. So it's negative 802 kilojoules. So if you burn, excuse me, if you burn 1 mole of methane, you will release into the surroundings 802 kilojoules of energy. Okay. So the methane is high in potential energy, and when you burn it, it releases that potential energy into the surroundings. Okay, so that is what that negative sign means there for the change in energy, but for this reaction. On the other hand, you have potassium perchlorate. Okay, when you dissolve potassium perchlorate in water, it is an endothermic reaction. It sucks heat out of the surroundings. Okay, so it has a positive sign. So you dissolve this in water. It will have to suck energy out of the water in order to dissolve, and thus the water will get cold. And so it has a change in energy of positive 51.0 kilojoules. Okay. So a lot of people get kind of backwards about endothermic versus exothermic. Do not think about it in terms of temperature. Think about it as the direction of motion of heat. Okay? So liquid freezing into a solid is an exothermic reaction, or an exothermic process, I should say. Gas condensing to a liquid, gas condensing to a solid. Those are all exothermic processes. You think liquid freezing, water freezes when it gets cold. Well, yeah, it freezes because it is losing energy to the surroundings. It's giving off energy. Okay, so therefore it is an exothermic process. And on the other hand, endothermic, solid melting to a liquid boiling to a gas, a solid subliming to a gas, photosynthesis. These are all endothermic processes. You think about water boiling. You know, you have a pot of water boiling on the stove. You take the water off the stove, it's going to stop boiling immediately because you're no longer putting energy into it. It's an endothermic process. So don't think about it in terms of temperature. Think about it in terms of the movement of energy. Which direction is that energy moving? If it's moving into the system, it's endothermic. If it's moving out of the system, it's exothermic. Okay, so recapping, system versus surroundings. The system is what we care about. The surroundings is literally everything else in the entire universe. Endothermic versus exothermic. Endo, it's moving into the system. Exo, it's moving out of the system. Okay. So that is it for, there we go, system versus surroundings. I will be back in a few minutes to talk very briefly about heat versus temperature.